Hey everybody, welcome to my session here at OSACon 2024. And my name is Alex Brissett, and welcome to Open Source and the Lakehouse. We're going to be talking about what open source has to contribute to the Lakehouse and how open source is powering the Lakehouse. But before we go there, let me just tell you a little bit about who I am and where I'm from. I'm from Dremio, which is the unified Lakehouse platform for self-service analytics and AI. We generally provide value to people who are implementing lakehouses in sort of three tiers of value, which include unified analytics, the ability to kind of connect all your different data sources between data lakes, databases, data warehouses, all in one place so that we can federate queries using our powerful SQL query engine that also enables really fast acceleration, along with our Lakehouse management features that include an integrated catalog that not only allows you to track your different data lakehouse tables, but also be able to have optimization of those tables, governance of those tables, and to be able to actually do versioning of those tables all from one place. So myself, I'm Alex Brissett. I'm a senior technical evangelist for Dremio, and I've spoken at many events like OSACon the past couple of years. I've spoken at Data Day Texas the past couple of years, Data Council. I'm also one of the co-authors of Apache Iceberg, the definitive guide from O'Reilly, and I'm actually just starting on my next O'Reilly book. So I spend a lot of time talking about the data lakehouse, as you'll see. And you can get a free copy of Apache Iceberg, the definitive guide, by scanning this QR code right here. And you can also just reach out if you don't get a chance to scan that QR code to get a free copy of Apache Iceberg, the definitive guide. I've also taught a Apache Iceberg crash course, which you can get access to by scanning this QR code here, all free. That way you get cool education. That's what I like to do. I like to educate people about the Lakehouse, about Apache Iceberg, about all these really cool technologies that we're going to talk about today, along with hosting several podcasts. All this stuff you can find over there at alexmerced.com. But with no further ado, let's get into the meat of today's presentation and start off with kind of setting that foundation of what is a data lakehouse. And to really understand what a data lakehouse is, you need to kind of understand what came before. So in traditional data systems, such as databases and data warehouses, the beauty of these tools is they kind of abstract a lot of things away from us. They abstract away how the data is stored, how the data that is stored is understood to be different data sets, different tables. How do we know which tables are available to us? And how do I write SQL and have that SQL parsed, then turned into an execution plan, and then actually have that plan executed? All that stuff is abstracted away from us, which makes these systems real nice because basically we can just go and put our data inside these systems and ask our data questions. Whether we're talking about databases, which generally store the data in more row-based formats for transactional data processing, or if we're talking about data warehouses, where the data is oftentimes stored in more columnar formats for more analytical data processing. But the problem is, because these systems are so integrated with all these layers, is that if I want to use more than one data warehouse or more than one database, I have to end up making a separate copy of the data into each system. Or if I'm in one really large enterprise where different departments are using different databases and different data warehouses, but we want to share that data to get like a 360 view of the company, you end up having to move that data around all these different systems, which can be very cumbersome, expensive, and delay your time to insight. So wouldn't it be nice if we just had sort of one sort of place to kind of have all the data? And there is a paradigm for this. It's referred to as the data lake, where the idea is we take the data from all these different systems that maybe different departments use, and we create a copy within files in a central storage repository known as the data lake, which is really mainly a storage layer. And then there are tools that can then run SQL or analytics against those files in that storage layer, which are tools like Dremio, AWS Athena, and many others. The problem is just with a pure data lake where you're just looking at a sea of files and storage, you don't get the same kind of guarantees that you get with a database or a data warehouse. You don't get that same sort of form of use of interacting with tables. Instead, you're interacting with files. That level of abstraction definitely makes thinking through your data and writing your SQL much easier. So how could we kind of get that? Well, what we need to do is introduce those missing layers of that database data warehouse abstraction. And that's where we start getting a data lakehouse, where we start inserting the missing pieces so that way when we interact with our storage, our data lake, it behaves more like a data warehouse with the same guarantees. So we just take the storage layer that we already have, like an object storage or HDFS. We take the compute tools that we're already using, like Dremio, AWS Athena, and then we add in a table format So that way that data now becomes, instead of a lot of different files, they become tables. And then we inject a catalog so that way we know which tables are available. And now when you connect to your data lakehouse, you're interacting with it as a list of tables that you can write SQL against, very similar to a data warehouse, but now you're working on that central repository. And now different teams can use their different tools that they prefer against the same set of data. Okay, so that's the idea here, is that different teams may prefer different compute tools, but the idea is that you have this open universal sort of format in this open place that allows each team to kind of work with the data in one place, even if they use different tools to interact with that data. Which basically allows you to kind of have that much more faster time to insight, those lower costs, the lower cumbersomeness, without necessarily having to sacrifice people's flexibility to use the tools that they like. Now, why does open matter? For a variety of different reasons. Innovation. Okay, the idea is that, hey, if we have one copy of our data, but different tools can use it, there's going to be more competition against those tools, driving those tools to be even better. Okay. The ecosystem. We have a much more larger variety of tools that we can use against our data when you have your data in sort of universal open formats, which again allows you to have much more flexibility. And cost. Competition drives costs down. You're going to have different options where you can optimize for the types of workloads you're running. So you can use, you can optimize for performance, optimize for cost. You can figure out, hey, how you want to optimize your workloads and which tools to use for those optimizations. So all of these are sort of really nice benefits of going to this sort of data lakehouse architecture, especially when you start getting into larger and larger scale data. Now, just because something is, let's say, open source doesn't necessarily always make it open. Okay, I mean, that's the first step, to have the code transparently available so people can see what the code is and understand what they're working with, or even self-manage instances of an application or a tool. But also it's being able to have an open and transparent contribution system where it's no longer, where there's not just one sort of institution that sort of controls or steers a open source project, but it's community run. And that's one of the benefits of the Apache Foundation, that they make sure that any projects that are part of the Apache Software Foundation portfolio are generally community, diversely contributed, open projects. So that way you do have a sort of project that's steered towards the community's needs, not an individual institution's needs. But this also makes sure that ensures sort of long-term development of the project, because there's many people who have an interest in the project living. And then open and transparent governance, where basically, what decisions even if you have a diverse community, being able to see what their decisions make out in the open and have open participation, whether they're public meetings, public email lists, all these kinds of things, then again, just allows the community and the ecosystem to really develop around that project. Now, there are several of these projects that have made a huge difference into the world of the data lakehouse. Okay, like the first one I'll talk about is Apache Parquet. So if we imagine that whole idea that there's all these different layers to our lakehouse, first we had storage. Well, I have to store the data in files in that. And the problem with like CSV and JSON is that they're going to be much bigger for the same amount of data. Okay, they're text-based. So there's no real way to intelligently sort of read them. You have to kind of read the whole file and then process the data. And the problem with that is when you start talking about really large data sets and you start getting to like petabyte-sized data sets, that can be really cumbersome, really slow. So Apache Parquet addresses a lot of the issues with traditional file formats for storing data, particularly CSV and JSON, and creates something that's optimized for analytics. Now, the first thing you kind of want to address is that oftentimes when you're using CSV, it's row-based, but you're storing different rows. And the problem with that, again, you oftentimes aren't doing row-based transactions when you're doing analytics. Oftentimes you only need one column. I might want to get the average height of all my users, and I just really need the height column. So it would be much more performant if the data for the height column was clustered together and I can just grab that independent of everything else. So that way I can just run that one calculation without having to load all this extra data into memory. Okay, so first off, you have a columnar format. So in Parquet, the data is organized into different columns, and you can grab those columns independently and read those columns independently without having to necessarily read the rest of the file. So that's like the first sort of big benefit that's going to speed up analytics right there. Now, these Parquet files, on top of that, what they're done is they're broken up into different row groups. Okay, so these are not individual rows, they're groups of rows. So in this case, it may, let's say, 1,000 rows. And then within that row group, you have the column chunk for each column within those 1,000 rows. Now, the benefit of this is that each row group has metadata. And the metadata for that row group allows a query engine, let's say like a Dremio, to be able to sit there and do what's called predicate pushdown. This means I can say, hey, you know what? I'm searching for only people between the height of 15, or let's say of 3 feet to 6 feet. I can see what the range of values for the height column for that row group is and determine whether I need to bother loading that row group at all. So by just reading a sliver of metadata, I could possibly skip reading a much larger chunk of data to make my scan much more efficient. Okay, so that's going to be benefit number 2. The metadata and the breaking up of the data into row groups allows us to more intelligently scan the file. Okay, and also within all of this, you get a couple other benefits when it comes to encoding and compression. The Parquet file format, because it's columnar, leads to much better compression, because when you take a look at like a sequence of a column, there's a better chance that you have repeated values or values in sequence that can then be used to do different types of compression and encoding to compress the file even further. So you have this really smart usage of compression and encoding to get the smallest sort of footprint of this data, and it's binary, so it's not text encoding. We're not using like something like UTF-8 or ASCII to encode the data as text, and then you have to interpret the text. The data is represented as sort of its own sort of unique binary encoding that can be done in a much more compressed space. So you have the binary representation, the encoding, the compression that leads to a much smaller file, so you can fit a lot more data in the same amount of space in a CSV or JSON file. You can scan that data much more intelligently because of that metadata chunked up in the row groups, and it's structured in a columnar way that leads to all of these things leading to just the quicker and faster ability to read that data from disk. Okay, so this makes it sort of the obvious choice when it comes to how do I store my data in the lake. But the problem is I have lots of Parquet files. So I might have a sales data set that's actually like thousands of Parquet files, because you're not going to make a petabyte sized Parquet file. You might have, 1,000 gigabyte file sized Parquet files. Now, how, and then actually let's say 100,000 gigabyte size Parquet files. So how would a tool like Dremio understand that these 100,000 files are a single data set? I could define it myself within my code, but then there leaves a chance that I might accidentally exclude a file or make some sort of mistakes, and you start having inconsistent definitions of the data in your analytics because of a typo or something like that. On top of it, because they're just files, you don't get the same guarantees when you're doing transaction across those 100,000 files. So it would be nice if I could look at those 100,000 files and understand them and think about them as a single table. Okay, and that's typically when we think of analytics, we think of data sets as a table, as a singular thing. And that's where Apache Iceberg comes in. Apache Iceberg is a table format. It's not a place to store your data. It takes the data you've already stored and wraps it together so that way it can be understood as a single unit. Okay, and the way it does this is through a chain of metadata. Okay, essentially you have 3 tiers of metadata. You have a metadata file that describes, hey, you know what, there's this table that exists, it has this schema, it's partitioned this way, and has these different snapshots. And if you want to scan the most current snapshot, well, here's the manifest list that has that particular snapshot. Okay, and within that manifest list, okay, so again, the metadata file defines the entire table. The manifest list is going to define the snapshot, and the snapshot is made up of a bunch of files called manifests. Each manifest is a list of files that are part of different versions of the table. Okay, so these manifests could be part of multiple snapshots, and the manifest list allows you to know, hey, this snapshot has these manifests. So at the manifest list level, I can see the list of manifests that make this snapshot along with the metadata on each snapshot. So kind of like in Parquet, you have metadata on each row group. I'm having metadata on each chunk of files at the manifest list level, and I can take a look at those same types of stats, because at the end of the day, the way this is done is you just take those Parquet stats and you roll them up to the file level, and then you roll them up to this manifest list level. And with those stats, I can say, hey, I don't even need this manifest. So right there, you've just eliminated the scanning of all the Parquet files in that particular manifest. So you're getting rid of chunks of files, not just chunks within a file, but chunks of files. And then once I've eliminated all the manifests that I need to read, and I go read the individual manifests, these manifests have stats on each individual file, and I can determine which files I need to read, and I can start just eliminating single files from my scan plan, from the list of files I need to scan to do my query. So now I have metadata that allows me to know that, hey, these 100,000 files are a single data set, but also provides me metadata to make sure I don't have to scan all 100,000 files. I can figure out, hey, which files I really need to scan for my particular query without ever having to touch those files to begin with. And then I only end up touching the narrowest subset of those files necessary. So giving me performance for these large petabyte scale data sets, okay, that are made up of lots and lots of Parquet files, but also giving me sort of transactional guarantees, asset guarantees, so that way I can truly treat those data sets in the same way I would treat database or data warehouse tables. Okay, enabling things like concurrent reads and writes, cool features around partitioning that are unique to Iceberg, because there are the table formats. Unique to Iceberg are things like hidden partitioning and partition evolution. And this all has to do with the fact that Iceberg tracks all of the partitioning stats within the metadata. So when it does partition pruning, it's not doing it based on, hey, how did you put the files in the file system, and you organize all the files into different folders for each partition. Instead, that data is in the metadata for each file. So it can look at that metadata for each file within those metadata files and say, this belongs to this partition. This enables a few interesting things. One, you can actually change how the data is partitioned if you want to eventually change it without having to rewrite all the old data. Because we can say, hey, these files were written with this partition scheme, and all the new files are written with this new partition scheme, and it can apply the appropriate logic when doing scan planning. You can, too, do transformation, or basically do partitioning on the transformed value of a column without necessarily having to persist another column in your data. In the past, if you wanted to take like a timestamp column and partition the table by month, you would have to create like another month column, and that column would exist in all your data files, increasing the storage of your data. Okay? That is not necessary here, because all those partition values can be stored in the metadata files, and basically the transform value will exist in metadata, but not necessarily exist in the actual files, because it's only used for partitioning purposes. Okay, and basically it provides you with these cool partition transforms. That's what hidden partitioning is. So the idea is that the partitioning logic and values are hidden away from the data itself. Okay, so you get the concurrent reads and writes, you get hidden partitioning, you get schema evolution, something you're used to in database and data warehouses, but not essentially a really easy thing in practice on the data lake. But now you make it really easy because it just works like a data warehouse. The data is automatically kind of optimized when you need it. You can run different optimization procedures that are already pre-made for you. And they have CDC features as well. Cool. And you get that better performance because you can do things like change how the table behaves through copy on write, merge on read, depending on whether you're optimizing for reads or writes. Okay, if you're optimizing for writes with a lot of upserts and deletes, then you might want to do merge on read. But if you're optimizing purely for read and you're not doing a lot of upserts and deletes, you might prefer to say copy on write. Okay, all sorts of other really sort of nice benefits when you are using Iceberg. So with Iceberg and Parquet, we've stored our data. Okay, I've stored the data in Parquet files. I've now been able to understand groups of Parquet files using Apache Iceberg, but I need when I load that data from those files into memory to do the actual processing, I want to load them in a way where I can store a lot of data in memory in the same way I can store a lot of data on disk with a Parquet file, so that way I can process a lot more data with the same computing power and the same memory, whatnot, basically use less resources to do more work. And Apache Arrow does that for representing the data in memory. So when you load that data from Parquet, Apache Arrow is essentially as Parquet is to the file storage optimization, Apache Arrow is to in-memory representation, where it makes it where you can store the same amount of data in a lot less space and process it a lot faster. It's an in-memory columnar format. And along with that standard, there's a bunch of libraries in every language that allows you to work with that format. So that way you can build in this faster processing into whatever tool. And nowadays, it started at Dremio. It was like originally Apache Arrow was the Dremio in-memory format before it was ever known as Apache Arrow or open source. And now it's become part of many data tools. Now, but the thing is that once you have the data processing quickly, you also need to be able to move that data between machines. And traditionally, you would move that data through like JDBC, ODBC, which was a row-based protocol. So you would have to convert that columnar data that's optimized, convert it into this unoptimized row-based format, and whatever time that takes to do that, and then convert it back on the other end. And that was another bottleneck. So to solve that, there's Arrow Flight, which is a protocol for transporting Arrow data across the wire. So that way, not only is the data on that machine being processed quickly, but it's moving quickly between machines. And this is designed to really kind of speed things up, to enable things like parallelism, transferring columnar data. And this actually has all sort of been even enhanced in a new sort of protocol called ADBC, which is kind of like JDBC, but like a columnar JDBC. And you can have different drivers for different tools to transfer columnar data, whether it's an Arrow or not. So overall, this project just keeps trying to figure out how to move that data faster and faster. And you can see an example here that the more rows you are transferring from one machine to another, the bigger this makes a difference. When it's like 2,000 records, not a big difference. But when you start getting to millions and billions of records, using Flight can make a huge difference in the performance of getting that data where it needs to be. Okay, so again, Aeroflight allows us, and then Aeroflight SQL is just another protocol to help you write SQL against and when you're using the Aeroflight interface. That just makes it easier to do your traditional analytics using Arrow data sets, so that way you get that extra performance without really changing the way you live life. Okay, and again, there's ADBC, and also there does exist, created by Dremio, an ODBC and JDBC driver for Aeroflight. So that doesn't let you just connect to Dremio using ODBC, JDBC and leverage Aeroflight, but allows you to connect to any Aeroflight enabled system like an InfluxDB as well, to get those benefits of that Aeroflight performance. So again, Arrow is the format which we represent the data in memory, Aeroflight being the way we move that data between computers. So that way you're constantly having to do as little movement, little transformation of that data, and packing that data as small as possible. Now, the final project I want to talk about is Project Nessie. This is a catalog. So I mentioned that we need a way to track the number of tables we have, and Nessie is that. It's a catalog. So again, we start off with columnar file formats that allowed us to kind of store that data at scale. Then we had open table formats that allowed us to wrap those data files into tables with guarantees. But then we need to track those tables, and another thing we want is to have data as code, to be able to do Git-like semantics on our data, so we can get things like isolation of our workloads, version control, be able to do governance, and sort of Nessie sort of fills that gap. So when you put all this together, you see you have a columnar file format, table formats, and then you have a catalog on top of that allows you to track all those individual tables. And it's that which the tools that you use interact with. So they would be interacting with the catalog, which could be Nessie. Nowadays, there's also something called Apache Polaris, Gravitino. There's a lot of different versions of this, but Nessie has some unique features. And what makes Nessie particularly unique is it enables versioning at the catalog level. So not versioning a single table, but the ability to version the state of the entire catalog, and to be able to branch and merge that in the same way you could do with Git. So you get those Git-like semantics and can work with your data in the same way you work with Git code and Git, but at the catalog level, which is pretty useful because you can just create a branch as a zero-copy clone of your data to allow for experimentation without having to duplicate your data. So it allows you to kind of prevent a lot of storage costs that come with making experimental environments, being able to easily say, hey, look, this ingestion job didn't happen correctly in this branch. I can just dump the branch and rerun that job again on a new branch and then merge it in when it runs successfully. Lots of other things like that to just ensure data quality. Okay, so again, you get that isolation, you get version control, and you get governance. And basically, this basically shifts away from that sort of single transaction multi-table transaction in databases where you do begin transaction and then you commit the transaction all at one time, to a world where you can actually do transactions across multiple sessions, across multiple engines, and isolate all of it. So we can create a branch in Nessie, do work across Kafka, a database, Spark, Dremio, Spark. Okay, we can do work across several different systems and not have to merge that till the very end, until we've done all those changes. Okay, and again, this works with several different tools because these are everything I've talked about in this presentation. These are open source projects that give you accessibility across all your favorite tools in the Lakehouse. With that, I hope you guys enjoyed today's presentation. Here I have a bunch of QR codes where you can get actually hands-on with a lot of these technologies that I've talked about by scanning these QR codes to try out these exercises. Here is a Slack community that I run. If you want to ask me any questions, keep in touch with me. It's called the Data Lakehouse Hub. And then here you can find a calendar of all the events that I'm speaking at or will be at, constantly updated with sort of where I'm going to be. So if you want to catch other events where I'm speaking at, you can scan this QR code. Thank you very much. Have a great day and enjoy. And again, make sure you can send me questions as well by joining the Data Lakehouse Hub Slack community. You can also find the link to that over there at thedataLakeHouseHub.com. Have a great day. Again, I'm Alex Merced from Dremio. Have a great day and enjoy your OSACon 2024.